Welcome to Power Machines N6. This is a velocity diagrams video. I know that many of you have been looking forward to this video, so I am going to try and explain it and make it as easy and clear as possible. What I do want to say before I start is that velocity diagrams are not difficult. I know that they look intimidating, but in reality, this is one of the chapters in Power Machines N6 that is actually really easy and really straightforward. So I really hope that after my explanation in this video, you will be able to see that this is actually a very easy chapter. I am going to help you to understand so that some of the statements that you come across in a question will not confuse you. Let's begin. So I am going to start by defining what is a stage. A stage is a combination of a row of fixed blades or vanes followed by a row of moving blades. And so what you see here drawn with blue rectangles is what are used to refer to the fixed blades. Okay, the row of fixed blades is what you see here with these blue rectangles. And the reason they call it the row of fixed blades is because these blades or vanes are not moving. They are fixed. They are already set at a certain angle so that they can channel the flow of gas in a certain direction. Hence, that row of blades is called the row of fixed blades because the blades are fixed. But immediately after that row, you have a row of moving blades. And this is what you see here in the gray area. It's a row of moving blades, okay? And these blades are moving. So when you have a row of fixed blades followed by a row of moving blades, that combination constitutes what we call a stage, okay? So in a gas turbine, a stage is made of a row of fixed blades followed by a row of moving blades. In Power Machines N6, you only studied single stage velocity diagrams, so you were just dealing with one row of fixed blades followed by a row of moving blades, and that was it. And for that reason, sometimes the row of fixed blades was also referred to as the nozzle because the gas was coming from the fixed blades and it was going into the row of moving blades. And so these fixed blades could be regarded as the nozzle, okay? But in Power Machines N6, what we have is two stages. So you have the first row of fixed blades followed by the first row of moving blades, and then you will have the second row of fixed blades followed by the second row of moving blades. And as you can see, if you understood my definition of a stage, when you have them following each other like that, this makes two stages, okay? So therefore, when you have to draw the velocity diagram of a two-stage gas turbine, you are looking at a situation like this. And so the flow of the gas is going to be in that direction from the nozzle. Remember, I said to you, the first row of fixed blades is also referred to as the nozzle. So when you are dealing with a two-stage velocity diagram, the flow of the gas will be from the nozzle into the first row of moving blades, out of the first row of moving blades, into another row of fixed blades, and out of the row of fixed blades, and then into the second row of moving blades, and out of the second row of moving blades, and out of the turbine, okay? So that is what you have when you're dealing with a two-stage gas turbine. Now, when we are drawing a two-stage velocity diagram, what we are really focusing on is that, what you see in this box. So you will have the first row of moving blades followed by a row of fixed blades and then a second row of moving blades. And when we are drawing the velocity diagram, we are drawing the velocity diagram of what is happening inside of this box. But even though we are drawing the velocity diagram of what is happening inside of this box, what is of real importance and what is really the focus is the first row of moving blades and the second row of moving blades. That is what is really the focus when we are drawing a velocity diagram. The row of fixed blades in between them is just a row that may affect the conditions of the gas before it gets to the second row of moving blades. But the velocity diagram is really about the first row of moving blades, and that is where we will draw the velocity diagram for the first stage, and then the second row of moving blades, and that is where we will draw the velocity diagram for the second stage. And so you will often see that you have a question that says the gas turbine has a row of moving blades followed by a row of fixed blades and then followed by a second row of moving blades. So the first row of moving blades will help you draw the first stage velocity diagram, and the second row of moving blades will help you draw the second stage velocity diagram. But in between them, you also have a row of fixed blades which may affect the conditions of the gas before it gets to the second stage. Really important. So now when you look at that picture, okay, you can make certain observations. The first one is the nozzle angle. Remember, this is the nozzle. The first row of moving blades is the nozzle, okay? The nozzle angle, okay, the nozzle angle will of course affect the angle of the gas because the gas is flowing through the nozzle. And so we can say that the nozzle angle here is also the same angle of the gas when it gets into the first stage. Okay, I hope you can see that. The nozzle angle is equal to the inlet gas angle into the first stage, because the gas is coming from the nozzle. So if the nozzle is inclined at a certain angle, then therefore the gas is also going to flow at that angle. And therefore we say that the nozzle angle is the same as the inlet gas angle into the first stage. You can see that when you look at that drawing. The second observation that we can make is that the outlet gas angle from the first stage, okay, the outlet gas angle from the first stage, we are here. The outlet gas angle from the first stage is equal to the inlet blade angle for the row of fixed blades, okay, as you can see. And the reason for that is to minimize the disruption of the flow of the gas. You want the angle with which the gas is leaving the first stage to match the angle at which the blades are inclined for the row of fixed blades, because the gas is coming from the first stage into the row of fixed blades. So you want their angles to be the same so that you will not have disruption in the flow of the gas. And that is why we say the outlet gas angle from the first stage is the same as the fixed blades angle at the inlet, of course, because it's at the inlet of the fixed blades, okay, of the row of fixed blades. This is the inlet of the row of fixed blades. So the outlet gas angle from the first stage must be equal to the inlet blade angle for the row of fixed blades. Okay, I hope you can see that. The third observation we can make is that the outlet blade angle for the row of fixed blades here, the outlet blade angle for the row of fixed blades must be equal to the inlet gas angle into the second stage. We want it to be that way to minimize disruption in the flow of the gas. So the outlet blade angle for the row of fixed blades is equal to the inlet gas angle into the second stage. And this is what we have here. Fixed blades outlet angle is same as inlet gas angle for second stage. Really important. Now, let us look at a two-stage velocity diagram. First, let me remind you of the picture that we just looked at. And remember what I said, when we draw the velocity diagram, we are really focusing at what is happening inside of this box. And so the first row of moving blades, that's where we will draw our first stage. The second row of moving blades, that is where we draw our second stage. But in between them, there is a row of fixed blades. And this row of fixed blades may affect the conditions of the flow in such a way that it will also be indicative of the situation of the flow when we are getting into the second stage. But as we begin to do examples, that will be very clear. And so when we are drawing a velocity diagram, remember, we use the subscript 1 for inlet conditions. So for instance, if I say V1, that will be the velocity at the inlet. And we use the subscript 2 for outlet conditions. So if I say V2, that will be the velocity at the outlet. Now, when you are drawing a velocity diagram, the first thing that you draw is the average blade velocity. And for that, we always draw a horizontal line like that. And then that line is, of course, a line that we will refer to as U, which is the blade velocity, or the average or mean blade velocity. And that is U, okay? Very important. And when we are doing a velocity diagram, what we really are doing is to draw velocities that are given in meters per second. We will represent them with lengths. And these lengths are in millimeters or maybe in centimeters, depending on the scale that you are given. So you will usually have a question, a velocity diagram question, and they may give you a scale, and they will say maybe 5 meters per second is equal to 1 millimeter.